In today's vanilla JavaScript text animation tutorial, we will learn how to take any word, letter, or sentence, and in 3 steps to convert it into interactive particles effect. We will learn how to give particles some motion physics and apply forces such as friction and acceleration. Then we will get the particles to form any shape we want, in this case letter shapes, and connect individual particles with lines similar to famous Particles.js library. But we will use no libraries. Everything we built today is from scratch using just plain vanilla JavaScript. I will explain all the code line by line, as I always do. Hi coders, welcome to my Creative JavaScript series, where we combine art with code, have fun building games from scratch, and learn front-end web development techniques in the process. This video is special for me because it's been exactly 1 year since I started my channel. As a celebration, I will take 2 of my most popular tutorials I have made for you so far, tweak them a little, and combine them into particle text animation you can see right now. Don't worry if you didn't watch these videos. As usual, we will build everything from scratch using just plain vanilla JavaScript, and I will explain every line of code as we go along. Coding section will have 3 main parts. In the first part, we will just create particles randomly spread around the canvas, and we implement some physics on them. We will apply forces like friction and acceleration and give each particle different weight to make the movement more realistic. Then, in the second part of this video, we will take these particles and shape them into letters or images. Both is possible with the code we will build today. And lastly, in the third section, we will take the famous constellations effect from Particles.js library, and we will connect particles that are near enough to each other with lines. But we will not use any libraries. We will write our own vanilla JavaScript code that does that. I just want to say well done, because if you are watching a video like this, you are already ahead of so many people. You could be watching a sitcom right now, which is fun as well, but you are here, learning new things, which means to me you are serious about developing your skills. I just wanted to say this because staying motivated on your learning journey is the single most important thing. So don't give up and keep pushing forward. Now let's talk about JavaScript. 2 of my videos that people seem to like the most are converting images into interactive particles and constellations effect from Particles.js library, but built from scratch with no libraries. I took parts of code from both of these tutorials, greatly improved mouse interaction movement by adding some physics, and created this text animation effect. You can make it into animated logo for your website, interactive background, automatic loading animation, and many more. This is creative coding, unlimited possibilities. You can use it for your coding portfolio to impress potential employers, or just as a coding exercise to practice your vanilla JavaScript and front-end web development coding skills. Let's take a closer look at the effect we are building today. We will write text on canvas, filter out certain pixels depending on their color or opacity, and convert coordinates of these selected pixels into particles. We will use array manipulation to store these particles as data, and using JavaScript ES6 classes, we create a custom set of particle objects for our animated effect. Once we have that, we can do whatever we want with them by giving them behavior using class methods. So I will make them interact with mouse and connect particles that are close enough to each other with lines. If you want to learn more about constructor functions, ES6 classes, this keyword, and get a complete comprehensive look about object-oriented programming in JavaScript, which is helpful for many particle effects we create here on the channel, there are some Udemy courses that really stand out for me. I will leave a link in the video description in case you are interested. If this is your first time here, hi, my name is Frank and I'm a self-taught front-end web developer. I learned everything I know in my free time from YouTube and online courses. How about you? I'm really wondering what kind of programmers are interested in creative coding videos like this. Do you study coding in school? Are you a self-taught programmer? Or do you work as a professional developer? How long have you been learning HTML, CSS and JavaScript? Are you getting ready to apply for your first coding job, or do you still feel you need more time to learn before you are ready? Or if you are more experienced, what kind of advice would you give to people who are just starting with JavaScript and front-end web development in general? Let me know in the comments, I want to know more about you guys. If you watch the video and code along with me, at the end I will show you how to create some interesting variations of this effect. Or maybe I will give you a hint and make it into a competition, let's see. Also, click the like please if you're getting any value from my tutorials. Let's start coding. In index.html, I link CSS style sheet, create HTML5 canvas element with an ID of canvas1, and I link script.js file, which will contain all JavaScript logic. In style CSS, I just do the basic reset to make sure the page appears the same in all browsers. Asterisk selector to target all elements on the page, and I set margin to 0, padding 0, and box size into border box. Border box means that elements padding and border will be included in its total width and height. On the body element, I set overflow to hidden to hide potential scroll bars and give it black background. I choose to place the background on the body element instead on the canvas, because this will allow us to use liquid or distortion SVG filters if we choose to. Especially liquid filter only works if canvas background is transparent. Canvas will have position absolute, top 0, left 0. Everything else will be done with JavaScript in script.js file. I create a variable I call canvas and I set it equal to document getElementById canvas1. CTX shortcut for context is equal to canvas getContext2D. Doing this will create a built-in context object that contains all kinds of 2D drawing methods that come built in any browser using Canvas API. Now I can call all of them using our CTX variable. Canvas width is the window in a width, and canvas height is the window in a height. This will make sure the canvas covers the entire browser window. I create a variable called particle array and I set it equal to an empty array. This will contain all our particle objects that each contains information like size, color, and coordinates. And we will pull this information from here to draw them on canvas. Before we do that, I will write some code to handle mouse interactions. I create a custom variable I call, for example, mouse, and I set it equal to JavaScript object by using curly brackets like this. I give this custom object some properties. X will be the current position of mouse on horizontal x-axis, Y will be position on the vertical y-axis, radius will be size of a circular area around the mouse within which the particles react to mouse. I create an event listener. It takes two attributes, type of event to listen for and callback function to run every time that particular event occurs. I want to listen for mouse move event. And every time user moves the mouse within the browser window, I want to run the following code. Callback function on event listener has one special thing about it. It has access to built-in object that contains all different details about the event that is occurring. All I need here are X and Y coordinates of the event so that I can assign them dynamically to our custom mouse object I created on line 8. I need to assign them to the custom object to pull that coordinate information outside of event listener so I can use this information all over our application. So as an argument to the callback function, I write down event. Some people just put letter E here. It doesn't really matter. JavaScript knows this variable will stand for that built-in event object and will let you use it whatever you call it here, as long as you refer to it using the same variable name later on. So inside the callback function, I set mouseX, which is property declared on line 9 to event.x, and mousey to event.y. If you console log event inside this event listener, you will notice it is quite similar to our custom mouse object on line 9. The only difference is that it contains many more properties and it is only available inside an event listener. That's why I am pulling the information from it here and sending it outside to our custom mouse object so that mouse coordinates are available all over our application, wherever I might need them later on. I can check if it works by console logging mouseX and mousey. Now if I move mouse over the canvas with open console, I can see we are getting values. Great. This is one of my favorite ways to handle mouse input. It is useful for everything from generative art, website interactions to games. Now let's draw some text on canvas. CTX font properties sets the current font properties for text context on the canvas. You can also set bold or italic here if you want. Then you put size and the last attribute will be font family. Let's just try 30 pixels Verdana for start. Now I call CTX fill text method, which will just draw and fill text on canvas. It expects at least 3 attributes. The first one is the text we want to write. I just put capital letter A for now. The second one is X coordinate on canvas, where you want to draw that text. The third attribute is Y coordinate. There is also an optional fourth attribute where you can define max width of the text in pixels. We will leave it empty for now, but keep that in mind. By default, the text will be black unless you set it to any other color using fill style property. So I call CTX fill style method and set it to white. Now we can see we are drawing our text at specified coordinates. I can change it by adjusting its size on line 21 or its position on line 22. Now, what I want to do is to scan a small area of canvas around the white letter A, analyze the pixels, filter out pixels with no opacity, because that's where the text is, and only save those pixels that are not transparent into our particles array. More specifically, I want to save their X and Y coordinates, and I can also save their color values if I want to. That way, we can replicate the shape of letter with particles by using X and Y coordinates of each pixel as coordinates for our particles. Remember that the black background is on body element, so canvas is completely transparent with only letter A having white color. To do this, I just use another canvas method called getImageData. We used it before to turn image into particles in one of my all-time most popular videos, and we will do something similar today with text. Official definition of this method is that it returns image data object representing the underlying pixel data of a specified portion of the canvas. If I want to say it much simpler, you give this method 4 coordinates for rectangular area somewhere on canvas. It scans that area pixel by pixel and it saves coordinates and color information for each pixel inside of a huge data array. Since we know how that data is organized, we can easily extract that information and use it for anything we want. So I create a variable I call, for example, data, and I set it equal to ctx.getImageData, and I pass it 4 attributes to tell it what part of canvas we want to scan. I want to start from top left corner, so coordinate 0, 0, and I want to scan just a small bit, let's say square of 100 times 100 pixels. So I pass it width 100, height 100, which is somewhere around here. If I want to visualize the area we scanned, I can just stroke white rectangle there so we can see. Stroke style set to white, stroke rectangle, and I pass it the same area I passed to getImageData method on line 25. See, this is the area we will be scanning, so our data variable on line 25 will contain array with coordinates and color information for each pixel inside this small square. Okay, let's delete this, it was just so we can visualize what's going on. Now I need a way to create many similar particles that will each represent one interactive dot in our final effect. For that, I will use JavaScript class. I call it particle with capital P. Each class has one mandatory method called a constructor. Constructor will run just once for each particle. It will create a new blank object and assign it properties and values based on information I will declare inside of it. It will serve as a blueprint. Our constructor will expect just 2 attributes, X and Y coordinates, which will be different for each particle, and we will pass them to the constructor from the outside to make it spell out our letters for the final effect. Inside, I just say this.x property on a new blank object you are creating is equal to X we passed as an attribute. Same for vertical Y coordinate. We will have other properties, but these will be set or randomized here inside the constructor. We don't need to add them from the outside, so we don't need to pass them as arguments on line 26. This.size will be radius of each circular particle, so let's try, for example, 3 pixels. I will also set this.baseX and set it to this.x, and this.baseY and set it to this.y. Base X and base Y properties will hold the initial position for each particle from the first time they appeared. The reason for that is that we will be moving and pushing the particles around by changing their this.x and this.y properties, but I want each particle to remember where it came from so it can return to its original position when mouse interaction ends. Also, I choose to set this.baseX equal to this.x property from line 27 instead of setting it to X attribute passed on line 26. It will be the same, but doing this will allow me to modify the starting position of this.x on line 27 like this, and our base x variable will remember that modified state. It can be used for interesting distortion effects. Not sure if we do it today, but there is no harm if we set up our code base for it anyway. This.density will be a random number between 1 and 30. It will determine how heavy our particles are and how fast they move away from the mouse. I want each particle to move slightly different speed to simulate some physics. So now the blueprint is complete. We will also need a custom draw method. Each of our particles will have access to it because it will be sitting on the particle class. This method will just take x and y and radius from the constructor and draw a circle there representing our particle. I set fill style to white. We are drawing a circle on canvas, so I need to use CTX begin path method. Think of it as pencil touching down on canvas to start drawing. I call canvas arc method and I pass it this.x and this.y coordinates. This.size will be radius of the circle, start angle will be 0, and end angle will be math.pi times 2, which is value in radians that actually converts to 360 degrees. So we have just drawn a circle path from 0 to 360 degrees, which is a full circle. If you change start angle and end angle values here, you can use arc method to create half circle or even many other shapes. I call close path and CTX fill to fill the path with white color. Now I create another custom function I call init. Its job is to take particle class we just created and call it many times to fill particle array with randomized particle objects. First I will set particle array to an empty array in case it's not empty at the moment. Now I call push method, which will take whatever we pass to it and pushes that to the end of the array we call it on. I pass it new particle. The new keyword is a special command in JavaScript. It will call constructor of its associated class. In our case, it will go up to line 26, create one new blank object, and give it values and properties as described in the blueprint between lines 27 and 32. On the line 26, we can see our constructor expects x and y coordinates as attributes. So here on line 45, I pass it 50, 50 as coordinates for now. Now I call init to push one particle into the array. I console log particle array to see if it works. I need to comment out line 17, that's still logging our mouse position. Yes. Now I can see the array contains one particle. I can add another one at coordinates 80 and 50. And now we have two particles in our array. I create a custom function I call animate, which will handle animation loop. First, I call CTX clear rectangle and pass it canvas dimensions to clear the entire canvas between every frame of animation. I create a for loop that will cycle through the entire particles array, and for each particle object inside that array, it will call its custom draw method we declared on line 34. The last thing I need to do is to call request animation frame and pass it animate, the name of its parent function. This way, animate will run all of its code and it will call itself again over and over, create an animation loop through a programming principle called recursion. So far I have just declared animate. I also need to call it to start our animation loop. It is not drawing our particles, and in console I can see we have error on line 37 where I misspelled arc. Fixed. Now we are drawing two particles as I declared them on line 45 and 46. I can change their x and y coordinates, and you can see they will move around as I change these values. So instead of calling the particles individually like this, I create a for loop that will run, for example, 10 times. I comment out the two individual particles, and inside the for loop I do the same thing. Particle array push, and I pass it new particle. It expects x and y coordinates, so I will create a temporary x variable. Its only job is to generate random number between 0 and 500. I do the same for y coordinate. Now I call new particle and I pass it temporary x and y variables I have just created on line 46 and 47. You can see we are drawing 10 randomized particles because for loop on line 45 runs 10 times. If I want the particles to be randomly spread all around the canvas, I can set x to a random number between 0 and canvas width, and temporary y variable to a random number between 0 and canvas height. Now our entire canvas is covered with particles. I increase the amount of particles to, let's try 500. Well done, we have base structure for our generative art project in place. First we declared global variables, then created object to store mouse coordinates. Then on line 25 we create a blueprint that will be used to create particles. Function init on line 43 will use that blueprint to fill particle array with particle objects. And lastly, we created animation loop on line 56, which is running over and over and redrawing our canvas for every frame. Even though it looks static now, we are actually drawing the same thing over and over. Let's make it move now. On line 35, I can change color. Let's try red. I create another custom method I call update. Its job is to calculate distance between current mouse position and current particle position. If they are close enough, I want particles to be pushed away from the mouse. Now I will show you how to calculate distance between 2 points. This can be used for creative coding and it is also very useful for games. Let's calculate distance between 2 points on horizontal x-axis first. I will call this variable dx. It is simply the difference between their position on x-axis. Let's say if mouse position x was 50 and particle position x was 30, dx will be 50 minus 30, which is 20. Simple, it's just the difference. Same for dy, which is the difference between position of two elements we are comparing vertically. We are comparing mouse against all particles one by one, so dy is mouse.y minus this.y. This.y stands for each individual particle, as we cycle through all of them one by one. Imagine these two values we have just calculated create a right angle triangle between mouse and particle. We have a dx side, we have a dy side of the triangle, and we know there is a right angle between them, so 90 degrees. We can get distance between these 2 points by calculating the longest side of the triangle, opposite to the right angle. It is also called hypotenuse. There is a built-in math.hypotenuse method in JavaScript, but today I will just use Pythagoras theorem to calculate it. We have two sides of right angle triangle, and we know there is a 90-degree angle between them. We need to calculate the third side, and that will be the distance between 2 points, which is what we need. Formula is mod square root dx times dx plus dy times dy, which is the same thing as mod square root dx squared plus dy squared. Since this is calculated inside update method on particle object, each particle will always be aware of how far away it is from a mouse. So here I can say if distance between particle and mouse is less than 500, run this code. If particles are closer to mouse than 500, I will set their size to 50 pixels. Else, this.size will return back to 3, which is the original value we declared on line 29. To run this code, I need to go inside animation loop and on line 68 inside for loop that cycles through the entire particles array for every frame of animation. The same way I call draw method for every particle, I will also call update, the method we have just created. And you see it works. Now I can change the distance particles react to mouse here on line 45. I can also create more particles on line 55. Now you can see the distance is being correctly calculated and we have a nice boilerplate for creative particle effect. We can do so many things now. Maybe if you want, before we continue, you can save and copy this code base in a different folder and experiment with it later on. It's always good to have the base setup stored away somewhere, and now you can just focus on your experiments. So what I want to do now is for particles that are close to mouse to start moving away from it. I want them to move from the center point of the circle towards the edge. I also want particles to move at different speeds depending on their weight. We defined earlier when we assigned this .density property inside particle class constructor. And third thing I want to happen is for particles to move fast if they are close to mouse, but gradually slow down the closer they are to the outer edge of circular interaction area, until they reach speed of 0 when they touch the outer edge. Basically, we will introduce some basic physics to particle movement. This might sound like a complicated thing to do with code, but I will show you a nice calculation that can do all of this for us. I create a variable I call force direction x, and I set it equal to dx divided by distance. Force direction y will be dy divided by distance. On line 48, if particles are closer to the mouse than 300 pixels, I will add force direction x to particles' current x position and force direction y to particles' current y position. This will just make them slowly move towards the mouse. If I multiply these values by, let's say, 3, it will make the movement faster. Now I want to set a distance past which particles' movement speed is 0. So I create another variable, I call it max distance. It will be equal to mouse.radius we declared on line 11. Any particle that is more distant from the current mouse position than this will stop moving. This calculation I'm about to do takes any range of numbers and converts it to a range between 1 and 0. It will convert values between 0 and max distance into a range of 1 to 0, just so I can multiply values on line 51 and 52 by this number and get the particles to slow down as the distance between them and mouse increases, until they reach speed 0 as they reach the outer radius of interaction circle around the mouse. So I will call that variable, for example, force. All I want to do now is to take number range of 0 to 250 and convert it to number between 1 and 0, depending on where on range between these two values the number is. 0 is particle with a distance 0 from the mouse, so it will be touching the mouse. I want this number to be converted to 1, so I can multiply current particle speed by this, which will make the particle move at its full speed. The second side of that range is number 250, which is represented by max distance variable. I want any particle that are further away from the mouse than this to have speed 0, so they stop moving. Let's say there is a particle halfway between 0 and 250, so this particle is roughly halfway between these values. It is 125 pixels away from the mouse. At that point, I want that particle to be moving at 50% speed, so I need force variable to be equal to 0.5 at that point. If I multiply current speed times 0.5, it will move at 50% speed. When particle reaches 80% towards the outer edge of interaction circle, I want it to move at 20% speed, so I want force to be 0.2. When particle is at 90%, I want it to be moving only at 10% of its original speed, and so on. To get this behavior, I need to convert range between 0 and 250, or whatever max distance variable is on line 48. I want to convert this range to a smaller range between 1 and 0. Once I have that value, I will multiply it times particle speed, and it will cause particles to slow down in proportions to its current distance from the mouse. You can already see the calculation. I say max distance minus current distance to see how far particle currently is from the max distance area. And once I have that value, I divide it by max distance again, which will tell me what proportion of max distance it is. Quick example, if max distance is 100 pixels and particle's current distance from mouse was 20 pixels, max distance minus current distance would be 80. Then 80 divided by 100 is 0.8, so our force would be 0.8. Basically anything multiplied times 0.8 is 20% less, so it will slow our particle down by 20%. I'm not sure if this is just me or this is quite difficult mathematical operation to understand. It took me a very long time to work this out. I will get back to this again and try to explain it better next time we use it. Let me know in the comments if it's unclear and we can talk about it. So now I have the force, which is a multiplier that will be slowing particles down as they get further away from the mouse. I create a variable called direction x, which will combine all factors that play a role in particles' movement speed. Direction x is equal to force direction x on line 46 times force we just calculated on line 49 times this dot density from line 33. I add this dot density into the mix because I also want individual particles to have different mass, and I want that value to affect their movement speed. It will look more natural. Otherwise, all particles will move the same speed as particles around it. I do the same thing for direction y. It will be equal to force direction y from line 47 times force, which will cause it to slow down as it moves further away from the mouse, times this dot density, which is individual and different for each particle. It's a random number between 1 and 31, as we declared on line 33. Now on line 53 I say if distance is more than mouse radius, which we declared on line 11, this dot x plus equals direction x variable from line 49, which combines all forces that pull and drag on our particle. And I do the same thing for particles vertical y position. This dot y plus equals direction y. That was calculated on line 50. It works, yay! Particles move slow at first and speed up as they get closer to the mouse. The only problem is that I want them to be pushed away, so I change plus sign to a minus sign on lines 53 and 54. Yes, this is good. And this is how you implement quite complex physics with JavaScript. I really like the movement, and we will enhance it even further, but don't worry, this was the difficult part. I'm not sure why I put mouse radius here on line 17 inside mouse move event. That's wrong. I will just delete that. Mouse radius is set to 450 pixels on line 11. If you look closely, particles move at full speed when they are close to the mouse, and when they get close to the outer edge of interaction circle, they move slower and slower until they stop. I can make them move faster by changing density. Let's try range between 50 and 200. You can change the movement speed by adjusting the range of values here on line 31. So on line 51, I check if distance between particles and mouse is smaller than a certain number defined in mouse radius. If it is, I push them away from the mouse. As you can see, particles stay where they are when mouse interaction ends. I would like them to return to their original position. So here on line 54, in else statement, I say if this dot x is not equal to this dot base x. Base x is defined on line 29 and it captures the initial position of each particle. So if this dot x has changed because we pushed particles around and it is no longer equal to base x, which is particle's original position, I will calculate distance between this dot x, which is particle's current position, and this dot base x, which is particle's original position on the horizontal x-axis. Once I know the difference, I can just return particle to its original horizontal position by saying this dot x minus equals dx. But to make particles move back slower, I say dx divided by 10. It will eventually get to its original position because this code is run for each frame of animation. It will just get there slower. Also keep in mind we are currently inside else statement, which will be entered only when particle is not close enough to the mouse. So particles will only try to return to their original position once mouse moves far enough from them. So this way we corrected particles horizontally. We can also correct them vertically. Notice I don't do else if here. I just do simple if statement because I don't want these to be mutually exclusive. If particle has been displaced on x-axis and also on y-axis, both of these statements will run for each frame of animation. But also they can just run separately in case only x-axis or only y-axis position needs to be corrected to return particle to its original position, as we saved this original position in base x and base y variables. So if this dot y is not equal to this dot base y, I calculate dy value. distance y value. And I adjust this .y by saying minus equals dy divided by 10. By changing values on line 57 and 61, I can change how fast particles return to their original position. So this all works. At the moment, we are just spreading particles randomly around the entire canvas area by calculating random x and y values here on line 70 and passing them as attributes to particles class constructor on line 72. How do we make the particles spell out letters of text? For that, we use data variable we declared on line 22. Here, we call canvas getImageData inbuilt method that takes 4 attributes for a rectangular area of canvas we want to scan, and it returns image data object that contains information like coordinates and color of the pixels from that area on canvas. Actually, let me rename this variable for clarity. I rename data to text coordinates. So now this variable I called text coordinates holds whatever getImageData method returned. I go down inside our custom init function, which at the moment runs a for loop 1000 times. Each time it runs, it calculates random x and y position and creates a particle there. I delete all this code because we don't want our particles to be randomly distributed around canvas. We have just scanned the part of canvas where we drew some text, and now I will filter that returned object that resulted from our scan, and I will remove all pixels with transparent background, leaving only data points for pixels that contain color, which will be coordinates for particles that make out our text effect. Keep in mind that canvas is transparent. The black color you see is set on body element, so the only pixels with color are the actual letters. Let's go through it step by step. I create a for loop, and I will do something a bit weird. Instead of just declaring one variable here as the first attribute, I declare 2 variables. I say let y equals 0, comma, y2 equals text coordinates.height. As long as y is less than y2, y++. This is almost a normal for loop. 2 things to mention here. First, yes, you can do this in JavaScript. You can put more than one variable inside a for loop. Also, I could have just declared y2 variable outside the for loop and it would work as well. Second thing is that I say y2 equals text coordinates height. Text coordinates holds image data object that resulted from us scanning small portion of canvas using getImageData method. This object has height property in pixels, and since I want to scan the resultant pixel data line by line, in this case row by row, I will run this for loop for every row of pixel data we have. So we declared 2 variables, and I say as long as y is less than y2, y++. Don't overthink this, we just have 2 variables. Y will keep increasing until it reaches the same value as y2. So our for loop will run until that happens. So this is analyzing pixels row by row. Each time I enter a row of pixels, I want to go through them one by one, from left to right. So I create a nested for loop, which simply is loop inside of another loop. Here I say let x equal 0, x2 is text coordinates width, which is simply just width of scanned area in pixels. In this case, we scanned rectangle 100 times 100 pixels, as you can see on line 22. So text coordinates height is 100, text coordinates width is 100 as well. This outer for loop will run 100 times, and each time it runs, it will run inner for loop 100 times. So we're gonna analyze 100 times 100, 10,000 pixels. I'll explain this further in a minute. Back on line 70, I say as long as x is less than x2, x++. This nested for loop might look complicated, but all it's happening here is I have a grid of 100 times 100 pixels. I go through them row by row on line 69. Each time I enter one row, I go through that row of pixels one by one until I reach the end. In this case, pixel number 100. Inner for loop on line 70 will exit. We jump back to the outer loop on line 69. Y will increase by 1, which will give us another row. We enter inner loop on line 70 again and go through all the pixels on that new row from pixel 1 to pixel 100. Then we exit the inner loop again, enter the outer loop, increase Y by 1, which gives us the next row, and we do this for all 100 rows, analyzing all 100 pixels in each row. As I said, we have 100 times 100 pixels because that's the area of canvas I have decided to scan using getImageData method on line 22. This nested loop basically allows us to cycle through every pixels in that 100 times 100 pixel area. For each pixel, I check if opacity of that pixel is more than 128. I will explain what that means in a second. Text coordinates custom variable holds built-in image data object that was returned by getImageData JavaScript method. This object has built-in data property, which is an array of elements that represent pixels from the scanned area of canvas. We can look inside by console login text coordinates. In the console, I can see it holds image data object. If I open it, you can see that object has a data property, and this data property holds a data array with 40,000 elements. More down, you can also see that it has height and width properties set to 100, which are the values we used in the nested for loops. Don't get scared, this is very simple. It is not a normal array. If you look closely, you will see this type of array is called something like uint8 clamped array. If I simplify this, it's a special type of array that can hold only numbers, and those numbers are limited to a certain range. You can say they are clamped. Each element in this array can only be a number between 0 and 255. If you work with HTML and CSS, you have seen RGBA color declaration, which looks like this. Any color can be created by combining different amounts of red, green, and blue, and the range for each color is from 0 to 255. One weird thing about this clamped array is that it also handles alpha or opacity this way. So 0 alpha is invisible, 255 alpha is fully visible. This is different because in RGBA color declaration, opacity is a small number between 0 and 1. So why does this array have 40,000 elements when the area we are scanning is 100 times 100 pixels? And we know 100 times 100 is only 10,000, not 40,000. Also remember that this is a special type of array called clamped array, so every element it contains can only be a number between 0 and 255. Again, very simple explanation. Let's look back at our RGBA color declaration. Each color is made out of 4 properties: red, green, blue, and alpha. Same with this clamped array data object. The way it's organized is every 4 elements in that array represent these 4 color values for 1 pixel. So color for pixel 1 is the first 4 numbers in this array. Color for pixel 2 is the next 4 numbers, and so on. That's why we have 40,000 numbers in this array and we only have 10,000 pixels. It's because we need 4 numbers to make 1 color. Each number is something between 0 and 255, including the number for alpha, opacity. That's why on line 70 I check if value is more than 128, which would be around 50% opacity. It's like halfway between 0 and 255, roughly 50%. Any pixels with more than 50% opacity will be added to our particle array. Each one will create a point in the final font shape. To extract these values, we have our nested for loops. If particle passed check here inside if statement, I create a temporary variable. I call it, for example, position x, and I set it equal to x, which is the variable from line 70, and it represents number of pixels in a row that passed our opacity check. I do the same for position y, which will be equal to y from line 69, which represents a row, vertical position of that pixel we are analyzing right now. So in terms of x and y coordinates, it's a vertical position of pixel that passed our opacity check. So I cycle through all pixels, I check their opacity value, and if their opacity is more than 50%, I capture their coordinates in temporary variables, position x and position y, and I call push on particle array, which is my custom array I created to hold particles for my effect. Push method just takes whatever we pass to it and places it at the end of array, so I pass it new particle, which will call particle class constructor that uses ESX class blueprint we created earlier and creates a blank object and assigns it values and properties based on the rules we declared in the blueprint. Our particular class constructor expects 2 values. to come from the outside for x and y coordinates, so I pass it position x and position y variables from lines 72 and 73. Remember that this code runs only when opacity is more than 50%, so only these particles from the scanned area will be added to our array. There is just one more little problem to sort out. As I said, clamped array that is held in text coordinates data object contains 4 elements for each pixel. We have 10,000 pixels, but this array has 40,000 elements. It holds value for red, green, blue and alpha for each pixel. Right now I am just checking one pixel because I passed index 1 in that array inside square brackets here. What I want to do is to cycle through the entire data array and take every 4th value, because I know every 4th value stands for opacity for each pixel. It's always red value, green value, blue value, opacity value, and so on. So I need to replace 1 with some code that will allow us to skip 3 elements, check the 4th one, skip another 3 elements, check the next one, and so on. One way to do this is I say in brackets y times 4 times data width plus x times 4 plus 3. Remember that we are inside a for loop, so y will be 1, then 2, then 3 as we cycle through rows, and x will be 1, 2, 3 as for loop cycles through pixels in each individual row. This calculation is not very intuitive. Just know what I'm doing is I'm cycling through 40,000 elements and always skipping 3 and checking the 4th one. I am not a math expert, so this took me forever to understand, but I think for now it's good enough for us just to show, just so you know what I'm doing. I'm sure there are simple calculations to log every 4th item in an array anyway. I will explore it more when we use this technique next time. That's it. This is how you scan a portion of canvas, filter out pixels with no opacity, and save their coordinates in your own data array. Since the font we scanned is very small, as you can see here, we don't want our particles to cover this small area. We want to spread them out evenly while keeping the shape of our letter A. So here on line 74, I just multiply position x times 10 and position y times 10. I made a small mistake on line 71. Earlier I renamed data to text coordinates, but here I still refer to it as data. Let me fix that. And we are drawing particles in the shape of a letter A. Well done, this is some advanced coding. I can change spread of the particles and therefore size of particle text by adjusting values here on line 74. Since we are taking particles from certain area and multiplying their coordinates to spread them around, it's not that easy to move the text left and right. But I can still do that by adding adjustment variable here on line 72 and also on line 73. I call them adjust x and adjust y, and up here on line 6 I declare them, and let's push x 10 pixels to the right and y 10 pixels down. Now you can move your particle text shape around anywhere you want by adjusting these two values. Size of the effect can be changed here on line 76. Let me just center it in the middle. And of course you can change the text we draw here on line 23. Some of you might like this effect already, but that's not all. I also want to connect particles that are close enough with lines similar to the famous Particles.js constellations effect, but on a text instead on random floating particles, and instead of using a library, we will write our code ourselves. I create a custom function I call connect. Its job will be just to cycle through the array of particles that make up our letter and measure distance between each particle. If they are close enough, we will take coordinates of the first particle and we draw a line to the coordinates of the second particle. That's it. Click like please if you're getting value from my tutorials. So I create a for loop that cycles through the entire particles array. Since this for loop will have to run for every frame of animation, let's optimize it a little bit. Normally I would just do nested for loops and I would compare every particle to every other particle in the same array. But I don't have to do that. The inner for loop only needs to cycle through the remaining particles in the array because all the particles before have already been compared in previous cycles of the outer for loop. I'm not sure if I'm explaining it clearly, but let's write some code and I will try again. So in the inner nested for loop, instead of cycling through the entire particle array again, just so I can compare every particle against every other particle, I will only cycle through particles that have a higher index than A, because anything with lower index has already been compared in previous cycles of the for loop. So here I say let B is equal to A, as long as B is less than particles array length, B++. If you look at line 96 again, when the outer loop runs for the first time, it will cycle through the entire for loop in the outer loop and inside the inner loop as well. But eventually, when variable A in the outer loop reaches number, let's say 50, in the inner loop, we say B is equal to A, and we cycle only through particles from index 50 to the end of the array. This will pair up all individual particles inside particles array. All I need to do here is calculate their distance and say if distance is less than some value, connect them with a line. We have already calculated distance between mouse and particles on line 45, so again it's exactly the same thing. Dx variable will hold distance between two elements we are comparing on the horizontal x-axis. Dy variable will hold distance between 2 points, in this case between particle A and particle B on vertical y-axis. This will give us two sides of right triangle, and we know that the distance between these 2 points is hypotenuse, the longest side of the right triangle, the side that is opposite to the right angle. To calculate it, we can use Pythagoras theorem formula, which we learned in school a long time ago. Math square root from dx squared plus dy squared, or in other words, math square root from dx times dx plus dy times dy. So to calculate the dx, distance of two particles on the x-axis, I say particle array A x minus particle array B x. A and B variables will be changing as we cycle through both for loops, so this code will compare every particle against every other particle by the time the for loop has finished. Dy will be particles array A y minus particles array B y. Now we have two sides of imaginary right triangle, and all we need to do to get distance between these two particles is to calculate hypotenuse, so math square root dx squared plus dy squared. Now I can say if distance is less than 100 pixels, I set stroke style to white because we want white lines. Line width will be 2 pixels, for example. On canvas, line is the same as arc we used to draw circle. It is considered to be a path, so to start drawing, I will have to call begin path. To draw a line on canvas, you need to call move to method to set starting x and y coordinates, and line to method to set target x and y coordinates. When you do that, a line will be drawn between these 2 points, each point defined by 2 coordinates x and y. So at first, I call ctx move to method, which creates a starting point of a new path at coordinates we passed to it. We are inside an if statement that only runs when two particles are close enough to each other, so I just want to draw a line from one particle to another. The starting point of the line will be x and y coordinates of particle A that passed our distance check. Then I call a line to in build canvas method. This method, simply said, creates a straight line from coordinates we pass to it to the last previous point inside the same path. Start and end of path on canvas will be defined by begin path and close path method calls here. So I call line 2 and I pass it x and y coordinates of particle B that passed the distance check. Now that you kind of understand how paths and lines work, you might be able to see that we can keep drawing more and more paths like this and create custom complex shapes, but I only want to draw a single line connecting particle A and particle B. All you need to do to create the popular Particles.js constellations effect with vanilla JavaScript is this code we just wrote from line 94. inside our custom connect function. We have just declared the function, we also need to call it inside our animation loop to actually run the code. So on line 90, I call connect, and here we go. This is just the basic effect. We can make it a little bit nicer than this. Here on line 105, you can change the distance limit. The limit will determine maximum distance between particles that get connected by white line. I think 50 looks pretty good, but for you it might be slightly different number depending on your base font and how much you decided to scale your particle shape earlier. Just try different numbers here and see what you like. One important visual thing that Particles.js library does is that the lines are not always fully visible. They don't just appear and disappear as particles move closer and away from each other. Lines slowly fade away and slowly appear again. Basically, opacity of the lines is dynamically calculated based on the distance between particles. It looks much cleaner that way. To do this in our custom code base is very simple. On line 96, I create a new variable called opacity value, and initially I set it to 1, full visibility. Then, here on line 107, I set stroke style to RGBA color declaration. RGB value for white is 255, 255, 255, and I will concatenate opacity value variable as the last fourth attribute for opacity, like this. Now we have a variable that can dynamically change, and opacity of lines will change with it. To make opacity proportionate to the current distance between particle A and particle B, I run this strange formula. Basically what I want is if distance is close to 0, particles are very close to each other, so I want opacity to be close to 1. As the distance between particles increases, I want to decrease the opacity value until particles are far enough and opacity will be 0. There are many ways to do this. Simple way is to say 1, which is full opacity, full visibility, so lines are visible, minus distance divided by 50. Notice that I divided by the same number. Don't overthink this. Let me give you two examples. If distance is 0, particles are close, line is fully visible. On the other hand, if distance is 50, 1 minus 50 divided by 50 is 1 minus 1, so 0. Lines are invisible when the distance between particle A and particle B reaches 50, or whatever you set the limit to. If you want particles to have 0 opacity when they reach maximum distance, keep these two numbers on lines 106 and 107 the same. If you change distance to 100, change the formula on line 107 to 100 as well. And the effect will work the same. Lines will still disappear when they reach or get very close to maximum distance. Here I am struggling a bit because I didn't notice I forgot one comma on line 108 inside RGBA color declaration. Just bear with me a bit. Nothing is changing about the code, I'm just trying to find the problem. Now I noticed the missing comma and suddenly everything works. What I will do now, I will copy these two lines and place them outside the if statement, which thinking back was not necessary because lines are only drawn if we enter the if statement on line 107. Now I just restore the formula to dynamically calculate opacity on line 105 and the base effect is done. Click the like please if you enjoyed this tutorial. Now it's time for a little challenge. If you want, you can change color of particles and lines around the mouse. Little hint on how to do that, we already calculated the distance between mouse and particles inside our update method. So somehow preserve that value, possibly as a new property on particle class constructor. And here on line 106, you can create multiple if statements and say if distance from the mouse is more than a certain value, change lines connecting the particles to a different color. You can do the same thing with color of actual circles that make our particles inside update method on the particle class, somewhere after the part where we calculate distance between mouse and particles. Also, if you decide to get creative and take this effect to the next level by combining it with something like liquid or displacement SVG filter we learned about in previous videos, or some other cool effect, let me know in the comments what you did and share the code if you want. I have a playlist with many original creative coding projects like this one. Everything in vanilla JavaScript, some quite advanced, some more beginner friendly. You can check it out if you want. Hope you had fun coding with me today. See you next time.